Hey, welcome back, everybody. How you guys doing? Oh, me, I'm doing pretty good. Thanks for asking. You guys, today's lesson, I think I'm actually going to return back to our book. I know we've been having like a little bit of like bouncing around with like different things we're posting, but I think at a certain point, I want you guys to be able to use your books as a resource. So today we're going to talk about solving trig equations using identities. So let's just say the title lesson is it's triggy. Okay, guys, there's tons of trig identities, and you can get super deep with these. Like a pre-calc really goes hard with trig identities. I'm not sure exactly how deep we're going to go with them, so I'm just going to show you guys a really basic one today. A basic trig identity comes from the unit circle. So if I pick any spot on the unit circle, like right here, then this height of the triangle is the sine value, and the base is the cosine value. And it has a radius of 1 because this is the unit circle. So it has a unit, radius of 1. You guys, once again, the sine is the height. Let's get some blue in here. So this is sine of theta. Remember, theta is like the rotation, how far we rotated. And then the base of the triangle is the cosine. So this is your cosine theta. Now, I want you guys to go up to an adult that has been out of high school for at least 10 years and ask them one high school math formula or equation that they remember. I bet you dollars to donuts, a lot of them will say a squared plus b squared equals c squared, which we all know is the Pythagorean theorem. Now, you guys, the Pythagorean theorem only applies to right triangles, but guess what? We've been doing nothing but right triangles for a long time. This guy right here is a right triangle, which means a squared plus b squared is equal to c squared, the hypotenuse. But if you look at what we already have here, like the height is the sine and the base is the cosine and the radius, the hypotenuse is 1. So, you guys, there's this thing called the Pythagorean identity. Which is sine squared plus cosine squared is equal to 1. It's a squared plus b squared is equal to c squared, but 1 squared is just 1. Now, this thing is super useful. It comes in handy all the time. Please know or realize that there's also rearrangements of this. Like if you were to subtract sine squared from both sides, you would get cosine squared theta is equal to 1 minus sine squared theta. So sometimes that version comes in handy. But if you go back to the original and maybe instead of subtracting sine squared, you subtract cosine squared, that means that sine squared theta is equal to 1 minus cosine squared theta. So this is the Pythagorean identity, but know that like sometimes the rearranged versions of it really come in handy. Okay, I'm going to do 2 problems for you guys. One of them is very straightforward, and then the other one is a little bit more in depth. First example, solve 2 cosine, that's not a cosine, cosine theta minus 1 is equal to 0 for 0 is less than theta is less than 2 pi. So they're just telling you what part of the circle it can exist on. You guys, first with all these problems, you're going to try to get the trig part by itself. So you can add 1 to both sides as your first step. So that means 2 cosine theta is equal to positive 1. Then you can divide off that 2 in front and get cosine theta is equal to 1/2. Now, you guys, you could grab your calculator and do like an inverse cosine and all that stuff, but really, we don't need to do all that. And, well, first of all, the calculator is only going to give you one answer, but there's actually multiple answers to this. So don't reach for the calculator. All you need to do is draw a quick unit circle and think about where cosine is equal to positive 1/2. The positive 1/2 should set off an alarm bell that that's a side in a 30, 60, 90 triangle. So I think that when the base is 1/2, that would be like right here. And if memory serves, this is pi over 3, where the base here would be 1/2. But, you guys, that's not the only spot that happens, because if you keep going around the circle, in quadrant 4, there is another triangle right here that also has a base of positive 1/2, a cosine of 1/2. So counting by pi over 3s, this is pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3, 5 pi over 3. So our two answers to this are pi over 3 and 5 pi over 3. So theta equals pi over 3 and 5 pi over 3. Final answers. They're both in between 0 and 2 pi. We're good to go. I've done examples like that for you guys before. We did a little bit of solving like this. So now let's definitely bump it up a notch. And this next example is solve -2 cosine squared x minus sine x plus 1 is equal to 0. Don't like that 0. And we're going on 0 is less than x is less than 4 pi. Whoa, going all the way out to 4 pi on this one. Okay. My initial thoughts and what you guys should be thinking about this. Do you see how there's cosines and sines like mingling in the same problem? A good strategy with solving trig is if you can get it all down into just one type of trig thing, you should do that. So instead of cosines and sines intermixing, it'd be cool if I could rewrite this in terms of just sine or just cosine. Now, let me scroll back up. The cosine squared, this guy right here, remember how I said that the Pythagorean identity can be rearranged? Look right here. Cosine squared of theta is the same thing as 1 minus sine squared theta. So what I can do is rewrite this guy as 1 minus sine squared theta, and then the entire problem is going to be in terms of sine. So that's going to be my first step. -2, 1 minus sine squared theta. Theta x doesn't matter. I guess I'll use x. I'll stick with the problem. Sine squared x minus sine x plus 1 is equal to 0. Distribute this -2. So we get -2 plus 2 sine squared x minus sine x plus 1. Now, some people try to subtract like these guys right here, but sine squared and sine are not the same thing. It's kind of like if you had x squared and x, you couldn't combine them because they're not like terms. They have different powers. So what can we do? Well, this -2 and positive 1 can be cleaned up. So let's just do a quick rewrite on that. 2 sine squared x minus sine x plus 3 is equal to 0. Now, you guys, at this point, wait, did I do that wrong? Yep, I did that wrong. -2 plus 1 is a -1. Minus 1 is equal to 0. Okay, you guys, this, what I've rewritten it as is a sneaky quadratic. It's really like this, and here I'll write it in highlighter and then get rid of it. If you had 2x squared minus x minus 1 is equal to 0, could you guys solve this? I hope so. It's a quadratic. No need to use the quadratic formula or anything like that. You could smoke and mirrors it if you want, or you could probably just guess and check it pretty quick. So what you need to do is think about this guy in terms of 2x squared minus x minus 1, and then you need to factor it. So what we can do is just pretend those are x's, and then it would factor, well, I guess I should write it off to the side, sorry. If it was 2x squared minus x minus 1 is equal to 0, this could factor into 2x times something, x equal to 0, and then I think it's 2x plus 1 and minus 1. Do a quick FOIL in your head to make sure. Okay, 2x squared, negative 2x plus x. Yeah, that does add negative x. And then a minus 1 on the end. So that's how you would factor it. Now, pretend that those x's, like these guys, are signs. So this factors into 2 sine x plus 1 times sine x minus 1 is equal to 0. Do you guys see how that's the same as this over here? But I replaced the x's with the signs. So we factored it. Now, normally, if you were solving this factoring thing, you would set both of those equal to 0. And that's exactly what we do here. We say 2 sine x plus 1 is equal to 0. And sine x minus 1 is equal to 0. So we have to solve both of these separately. Once again, get the sine part by itself. So with the left-hand one, you would subtract 1 and divide by 2 to get sine of x is equal to negative 1/2. Now that negative 1/2 should look familiar to you because, once again, that's a side in a 30, 60, 90 triangle. So we need to figure out where on the unit circle you have sine values of negative 1/2. Oh, but wait, what's our domain? We have to go all the way out to 4 pi. Whoa, interesting. Okay. Negative 1/2 would be here when the height of the triangle is negative 1/2. But that also happens in quadrant 4, right here, where this is negative 1/2 as well. So if I count by, what are those, pi over 6s? So that's like 6 pi over 6. That means this is 7 pi over 6, and this is 11 pi over 6. But then you have to go all the way around the circle again. So here, let's keep track of this. The first one was 7 pi over 6, and then the second one was 11 pi over 6. So that's where the sine is equal to negative 1/2. But the domain, they want me to go out to 4 pi for some reason. So what we need to do is keep going around the circle. So like if you keep going past 2 pi, and then you come around here again, we need to figure out what this spot is going to be in terms of pi over 6s again. There's a lot of ways you can do that. I just think of it as basically it's 7 pi over 6, but with a full circle around again. And a full circle is 2 pi. But 2 pi in terms of pi over 6s is 12 pi over 6. So that means if you take 7 pi over 6 and add 12 pi over 6, the next spot would be 19 pi over 6. That's the same spot as this, but just going around the circle one more time. Same strategy with this guy right here. Think about going around the circle one more time. So it's 11 pi over 6 plus another full 2 pi, full circle, which is a full 12 pi over 6s. So 11 pi over 6 plus 12 pi over 6, I believe, is 23 pi over 6. Yeah. Whew. Now, you guys, that was just solving this guy right here. But I haven't even touched sine of x equals minus 1 equals 0. So we have to solve this guy too. Sine of x is equal to positive 1. If you think on the unit circle where sine is equal to positive 1, this is not too bad. But once again, you have to go from 0 to 4 pi. Positive 1 is when you get that really skinny triangle up here at the top, when it's like all height, no base. And that is what? Pi over 2. But then we have to go full 2 pi around again because it's from 0 to 4 pi, not just 2 pi. So adding on a pi over 2, there's one answer. Adding on a full 2 pi to that, 2 pi in terms of pi over 2s is 4 pi over 2. So I think this would be 5 pi over 2. Now we jam it all together and say that x is equal to, do we have to put them in order? Sure, why not? Pi over 2, 7 pi over 6, 11 pi over 6, 5 pi over 2. You don't have to put them in order. I'm just doing it for fun. Isn't this fun? 19 pi over 6 and 23 pi over 6. Woof. Long problem. Okay, you guys, I think I'm going to leave it there and just assign you some problems back from your book. Remember that the worked out solutions are in the files section of your Canvas, so definitely use those as a resource. Yeah, okay. Hope you guys are doing well. HMU via email if you need some help with anything.